In this video, we'll look at the answers to the GCSE Chemistry paper, Unit 2, 2023. Question 1, it's a nice question here. We have to complete this table, which is about the reactions of metals, potassium and copper, with oxygen and with water. Potassium, heated in air, is already completed for you. So let's look at the copper one. Now, I would suggest that you follow the same pattern as is given to you. So if you look here, it's the appearance of the potassium metal to start with, what happens when it burns, and then what the product looks like. So to start off with, then the copper, what is the appearance of the copper metal at the start? Well, copper is a brown solid. You could also say orange solid, orange-brown solid. I'll just stick with brown solid for now. Then on to the next part, where we're looking at what happens when it burns. Well, the copper metal, when you put it into a blue Bunsen flame, you will see a blue-green flame. Think back to year 11, when you did the flame test, copper has that blue-green flame. Now, don't say blue or green on its own. And then the final thing is what the product looks like. So again, we've got it for potassium with the white solid forming. For copper, you get copper 2 oxide, which is black. Well, just to point out here that copper, when you put copper into a blue Bunsen flame, it doesn't actually burn the way potassium would, but it does react with the oxygen. On to the next part of it, a balance symbol equation for the reaction of potassium with oxygen. Potassium's K, oxygen is O2, it's a diatomic molecule, and then we get potassium oxide. It is the formula K2O, and you should be able to see that it needs to be balanced. 2 in front of the K2O, that will now give 4 potassiums, so 4 is required over on the left. Copper doesn't react with cold water, but potassium is very reactive with cold water. Now, there are a number of things you could have here. I'm just going to write in some of them. So, for example, you could have floats, fizzing, heat's released, colourless solution formed. Now, that should be enough. You could also say the metal disappears, it burns with a lilac flame, it melts into a ball, there's a crackle at the end. Lastly, a balance symbol equation for the potassium reacting with water. So K plus H2O, that'll get you 1 mark. That goes to give potassium hydroxide and hydrogen. So that would be a mark. And then a 3rd mark for balancing it. Part B is about phytomining. So we have to describe phytomining in 4 steps. Now, you can keep this simple. So step 1 is where copper compounds are absorbed by the plants. And those compounds will be absorbed through the roots. Now, you must have copper compounds, or you could say copper ions, but don't say copper on its own. Then on to step 2, the plants are burned to an ash. Step 3, an acid is added. Now, this might typically be sulfuric acid, but it could be other acids as well, like hydrochloric acid. This means that the copper compounds will react with the acid. So say, for example, react with the sulfuric acid to form copper 2 sulfate. And the final step is getting copper then from that solution. A displacement reaction takes place by adding iron. And for that, you'd need the iron and displace in there to make sure you get the mark. And of course, this reaction happens because iron is more reactive than copper. On to C, part 1. We have to use the table to put the metals in order of reactivity, and we're starting with the most reactive one first. Well, the way we work this out is to see which metal has the most ticks. So we can see from magnesium that it has 3 ticks. Now, I'm not looking across this way. These are the metal solutions. So just be careful with that. We're looking down the way. Magnesium has 3 ticks. Zinc has 2, Well, as you can see, silver doesn't have any, and the lead has 1. This means that magnesium is the most reactive, then zinc, lead, and finally silver. Part 2, a balanced simple equation for the reaction between magnesium and silver nitrate solution. Well, magnesium is obviously Mg, silver nitrate is AgNO3. Magnesium is more reactive than the silver, so you get a displacement reaction. This then needs to be balanced. You can see you've got 2 nitrates on the right. I need 2 nitrates on the left, so we need to put a 2 there. That now gives 2 silvers. A 2 then is required on the right. Part 3, we have to explain the reaction between magnesium and zinc nitrate in terms of electrons, and explain why this is a redox reaction. Now you need to be careful here, because it might be easy to think that the reaction is about magnesium and silver nitrate, which was the previous question, but it's not. It's magnesium and zinc nitrate. Now this type of question always follows the same pattern. A metal always loses electrons and a metal ion gains electrons. Well, the metal in this case is magnesium. You see, it's not bonded to anything else, it's just magnesium, so this is going to lose electrons. You then have to give a definition of oxidation. So oxidation is loss of electrons. Remember, don't say magnesium loses electrons and this is oxidation. You must give a clear definition of oxidation. And I'm using oil rig to remind me of the oxidation and reduction processes in terms of electrons. Okay, the next step then is to deal with the zinc ions. So you've got zinc nitrate, this is ionic, it's made up of zinc ions, and they are going to gain electrons. But be careful here, you can write the word zinc and then put ions after it. If you're writing the symbol, it must be the proper ionic symbol. Do not write Zn ions, because this is obviously the symbol for an atom of zinc, and it's the ions which gain the electrons. The zinc ions gaining electrons is reduction, so you have to write a definition of reduction. And the final thing to do in this type of question is explain what redox is. Question 2a, part 1. What do you understand by the term reversible? That just means that the reactants can go into products and the products can change back into reactants. Now you could write a simpler definition here, something like the reaction can go in both directions, or the reaction can go forwards and backwards. And you can see that due to the reversible sign. Part 2 then, an equilibrium question. So explain why the equilibrium yield of the SO3 decreases as the temperature increases. Well, in the introduction to the question, we're told that the forward reaction is exothermic. So this direction releases heat. That means that if the temperature is increased, the system will try and reduce that increased temperature, and so it will move in the reverse endothermic direction. If the forward direction is exothermic, then the reverse direction is endothermic. So let's answer this question then. And equilibrium questions always require the position of equilibrium to be mentioned. So the position of equilibrium will move to the left in the reverse endothermic direction. Part 3. Explain, so we have to state and explain how an increase in pressure will affect the yield. Okay, so let's go back up to the question, and we can see that there are 3 moles of gas on the left and 2 moles of gas on the right. Now when pressure is increased, it always moves the position of equilibrium from more moles to fewer moles. So in this case, the position of equilibrium will move to the right. which means that the yield of SO3 will increase. Instead of saying to the side with fewer moles of gas, you could say it moves from 3 moles to 2 moles of gas. Don't say that it moves to the side with fewer particles or to the side with fewer species. Part B is about zinc metal reacting with sulfuric acid, and we've got 0.26 grams added to a volume and half moles per cubic decimeter sulfuric acid at 20 degrees C. So we can see the results that were obtained when the volume of gas, which would be hydrogen gas, is recorded every 10 seconds. So we'll move on then to the first part of the question. Write a balancing equation for the reaction between zinc and sulfuric acid. Well, zinc is Zn, sulfuric acid is H2SO4, zinc sulfate is formed, and hydrogen gas is produced. That would be 2 marks, one for the left hand side, one for the right. It does ask us here to include state symbols. Well, zinc metal is obviously a solid. The sulfuric acid is aqueous, it's in solution. The zinc sulfate formed will also be in solution, so it's aqueous, and hydrogen is a gas, so we put a G. Part 2. The experiment was repeated using zinc powder. Now, if you can make out on the right, which was the start of the question, zinc granules were used. Now, the powder has a larger surface area, so that's going to mean that the rate of reaction is increased. If the surface area is increased, that means that there will be more successful collisions. And the final thing in for the 4th mark, which all rate explanations require, is per unit time. Or of course you could put in per second, per minute, or in a given period of time. See part 1. Explain how a catalyst increases the rate of a reaction. Now, this is not giving a definition of a catalyst. This is asking you to explain how the catalyst actually works. So here's the first point. It provides an alternative reaction pathway. Be careful here. Alternate is not correct. It must be an alternative reaction pathway. And the word reaction is vital as well. Okay, so don't leave that out. And this alternative reaction pathway has lower activation energy. Now, don't write low activation energy. It must be comparative compared to without a catalyst, so it's lower than the original. Part 2 then, we'll have to sketch this graph. If the experiment is repeated using 1 gram of copper 2 sulfate. Now, copper 2 sulfate, we're told up here, is the catalyst. It's going to speed up the reaction, but catalysts do not increase the yield. It will start at 0, 0. It's going to be steeper because the rate of the reaction will be increased, but it will level off at the same place as the original. Question 3. We're moving on now to organic questions. So crude oil is a mixture of hydrocarbons. Part 1, name the process used to separate crude oil. Well, when you want to separate liquids that mix with each other, or miscible liquids, fractional distillation is used. Hydrocarbon, well, you can see it's made up of hydrogen and carbon. So it's a compound or a molecule containing hydrogen and carbon only. Just be careful here, don't say a substance. We'll just stick with compound or molecule. B part 1, what is meant by the term homologous series. Okay, so these are the points that you could include. Any 3 of those points will get you the marks. Part 2, general formula of alkanes is going to be CnH2n plus 2. Part C, this is about cracking. And cracking is where long chain alkane molecules are broken into shorter alkane molecules, and an alkene is also formed. Now, the thing to remember here is that the left hand side has to equal the right hand side. You can see that on the right there are 14 carbons. That means there have to be 14 carbons on the right. Well, we already have 12. That means that we need another 2. We'll do the same sort of thing for the hydrogens. There are 30 on the left. We need 30 on the right. So far there are only 26, and that means that another 4 are required. So the formula is C2H4, and that would be ethene. Part 2, reaction profile diagram for an endothermic. So that means that the products will have a higher energy than the reactants. I'll start off with the reactants down here and put the products up here. Now we have to show the reaction progress, or the reaction pathway. It's also asking us to label the axis. The y-axis is going to be energy, and the x-axis is the progress of reaction. Now, one more thing to do is to label the activation energy. Well, activation energy always goes from the reactants to the peak of the hump, or the peak of the reaction pathway. So it's going to be from here all the way up to here. The question does indicate that it has to be labelled, so I'll just write that in. Now I want to just do one more thing here. For energy level diagrams, you have to put in the reactants and products. On the reactant, now this is based on part 1, so the question above. The reactant is C14H30, and it gets broken into C12H26 and C2H4. Part 3, state the meaning of the term activation energy. So this bit here, that's the minimum energy required for a reaction to occur. Or you could say the minimum energy required for a reaction to take place, or for a reaction to start. So if particles don't have the activation energy, then nothing happens. The particles just bounce off each other and no reaction takes place. On to part D. They have to use the bond energies to calculate a value for the bond energy of one carbon-carbon bond. Now, in this type of question, the way we work it out is that the energy change is the total of the bonds broken in the reactants minus the total of the bonds formed in the products. I'm just going to sketch out the table, and in here I'll put the bonds broken, and here will be the bonds formed. I'm trying to work out the carbon-carbon bonds, and there are 2 of them. So we'll just put in 2 carbon-carbon bonds. The next one then is the carbon-hydrogen bonds. So let's see how many of those there are. 1, 2, 3, 4, 5, 6, 7, 8. So that's going to be 8 times 412. And then we've got oxygen double bond, and there are 5 of those. So that's going to be 5 times 496. Now on the right hand side, there are carbon-oxygen double bonds, and you can see that per carbon dioxide there are 2 of them. There are 3 molecules, so in total there will be 3 times 2, which is 6 carbon-oxygen double bonds. So that will be 6 times 803, and that works out to be 4818. And then the OH bonds, well, there are 2 per molecule of water, but there are 4 water molecules, so it's going to be 4 times 2, which is 8. So we're going to multiply the 463 by 8. So there are 8 OH bonds, and that works out to be 3,704. Now we can put this into an equation. Well, the energy change is minus 2,050 kilojoules. So that equals the bonds broken minus the bonds formed. So that's going to be 2 carbon-carbon bonds. Remember, that's what we're trying to work out. Plus the total of these two. So if we just add these two together, that works out to be 5776. And we'll subtract the total of the right hand side. So again, just add these up, and that works out to be 8522. I can now rearrange the equation. Don't forget, when you move a value from one side to the other, the sign changes. That works out to be 696. Remember, that is for 2 carbon-carbon bonds. So a carbon-carbon bond, then we just simply divide the 696 by 2. And that will give a value of 348 kilojoules. Part 1, the molecular formula of lactic acid, which we have here. So you can see it's a carboxylic acid, contains this carboxyl group. It can be written as CXHYOZ. What are the values of X, Y, and Z? Well, you just simply have to count up each of these. Well, X is going to be for the carbons. There are 3 carbons. So just simply put in 3. Y is then associated with the hydrogens. So count those up. 1, 2, 3, 4, 5, 6. And lastly, Z, which is associated with the oxygens. Well, there are 1, 2, 3 oxygens. Part 2, draw a circle around the carboxylic acid functional group. This is the functional group. Part 3, explain the meaning of the term weak acid. Well, a weak acid is partially ionized in solution. And you can see that the word associated can be used instead of ionized, or water can be used in place of solution. Part 4, if you have copper 2 carbonate and it's added to a solution of lactic acid, 3 observations that you would make. Well, this is just a typical carbonate and acid reaction. Carbonates always fizz when added to an acid. A copper carbonate is green. Anytime there's a colour change in a reaction, you can write that as an observation. So the green solid, or the green copper 2 carbonate, disappears. A colourless solution is not obtained here because it's not a group 1 or a group 2 compound in solution. It's a transition metal. And we know the compounds of transition metals are coloured. Copper solutions are usually blue. So I'm going to put in blue solution formed. F, part 1, draw the structural formula of propan-1-ol. Now this is an alcohol because it ends in OL. The prop tells us that there are 3 carbons, 1, 2, 3. And this number tells us where the hydroxyl group is, or the OH group. It's in carbon number 1. Now I could have put it on the other side. It's just the same molecules that I've drawn, only turned over. I could also have put the OH up here or down here. It doesn't matter as long as it's attached to the first carbon. And then the other thing that has to be done is complete the molecule by drawing hydrogens attached to the carbons. Part 2, name a reagent that may be used to oxidize an alcohol to a carboxylic acid. Well, that is acidified potassium dichromate. Part 3 follows on from this. Name the carboxylic acid formed when propan-1-ol undergoes oxidation. Well, propan-1-ol will oxidize to propanoic acid. G, part 1, what is meant by the term polymer? Well, a polymer is a long chain molecule made up of repeating units, or made up of small molecules. Part 2, I have to name this polymer. Well, the polymer is always based on 2 carbons. So you can see here and here, and there are only hydrogens around it. So that means it's based on ethene. The polymer, therefore, is polyethene or polythene. Part 3, therefore, it's polyethene. Got to draw 2 carbons with the 4 hydrogens around it, and we don't include these bonds because then carbon would have too many bonds. So just make sure that the carbons have 4 bonds around them. Question 4 is about electrolysis. So we're just going to A, part 1. What name is used for the liquid that conducts electricity and is decomposed? That's an electrolyte. Part 2. How would you know when the molten lead-2 bromide was conducting electricity? You can see from the diagram that there's a bulb. That bulb will light as soon as the molten lead-2 bromide starts conducting electricity. If you looked at the mixture in the crucible, you would also probably see a red-brown gas being produced. So that would be acceptable too, and that would indicate that the reaction is occurring. So not just gas on its own, but a red-brown gas, because obviously it's lead-2 bromide, and the bromide ions would be converted into bromine gas. Part B. Name the type of reaction shown. Well, the lead-2 ions are gaining electrons, and reduction is the gain of electrons. So this is a reduction reaction. Part 2, write a half equation for the reaction occurring at the positive electrodes, that's the anode. So lead ions go to the cathode, that's where reduction always happens. Oxidation occurs at the anode. I'll draw the anode out. That's plus, and this is where the bromide ions migrate to or are attracted to. Obviously they're minus, going to be attracted to the positive electrode. Now each bromide ion loses an electron and is turned into a bromine atom. And that happens twice. So we get 2 bromine atoms formed. They combine to form a bromine molecule. So the equation which occurs is 2 Br minus goes to give Br2 plus 2 electrons. And it's usually written that way. You could have put the electrons over on the left. So just to say, you could also have that. Part 3, what's observed. I've already referred to this. Because bromine gas is given off, you're going to see a red-brown gas. I don't say red or brown on its own. C, part 1. A word equation for the reaction which occurs when molten lithium chloride is electrolyzed. Well, we're going to start off with lithium chloride, and it is going to decompose into lithium and chlorine. Now just be careful here that you don't write a balanced symbol equation. So word equations, if you write a symbol equation, it will be wrong. Part 2, just going to the question part. What term is used to describe electrodes that do not take part in an electrolysis reaction? Well, those electrodes are inert. Part 3, name a substance which could be used to make the electrodes. Well, we usually use graphite. That's what would be used in the lab because they're relatively cheap. You could also use platinum, but of course platinum would be much more expensive. Part 4 then, explain how molten lithium chloride conducts electricity, and this applies to all molten ionic substances. It has to do with the ions. So when molten, the ions can move and carry charge. Question 5, part A, is about a titration, and you can see here, looking at the bullet points, we'll have to describe in detail how the burette is prepared and filled with a solution of the acid. And then we have to describe how steps are taken to ensure accuracy when determining the end point. Let's look at how this burette is prepared and filled. Well, the first thing that we would do is rinse the burette with the acid. It would then be filled with the acid. And we want to make sure that the jet is filled, that's the part below the tap. We could also say there, ensure there are no air bubbles. So those first 3 points then cover how it's prepared. You may have some other things in there or slight variations of it. So for example, where I've got fill the burette with acid, you could say fill it until the bottom of the meniscus is at 0.0 cubic centimeters. But these 3 points are fine. So now I'll move on to accuracy. The volumes have to be read from the bottom of the meniscus. Then we want to add the acid dropwise near the end point. And a final thing we could put in here is swirl the flask, because obviously we want to make sure that the reagents are thoroughly mixed with each other. Just be careful here that you use the word endpoint and don't say add dropwise near the end of the reaction. It has to be endpoint. On to the calculations of part B. Calculate the number of moles of sulfuric acid used. So we'll go up to here and see that 25.0 portions of the solution were titrated against 0.2 moles per cubic decimeter of sulfuric acid. And the average titer was found to be 24.2. So this 24.2 is the sulfuric acid. It's going to be 0.2 times 24.2 over 1,000, and that equals 0.00484. Now, just in case you're not sure of what values are applying to the sulfuric acid, we see here that 6 grams of the carbonate was dissolved in the water and made up to 250 in a volumetric flask. If I draw the volumetric flask, that's 250 cubic centimeters, and that's the 6 grams. And then 25.0 cubic centimeters portions of the solution were titrated. So that means that the 25.0 cubic centimeters were put into the conical flask and titrated against the sulfuric acid. Now on to part 2. Calculate the number of moles of sodium carbonate present in the 25 cubic centimeter solution. For this we use the equation, and you can see that it's a 1-to-1 ratio. So they're going to be the same number of moles as the sulfuric acid. Part 3, calculate the number of moles of sodium carbonate present in 250. So back up to the diagram. We have just worked out that there are 0.00484 moles in this 25 cubic centimeters. So now the question is asking us to calculate the number of moles in 250. Well, to go from 25 to 250, we're multiplying by 10. Therefore, we'll have to multiply this value by 10 because there are going to be 10 times as many moles in here as there are in here. So our answer here is going to be 0.0484, or you could put 4.84 times 10 to the minus 2. Part 4, using the initial mass, well, that was 6 grams. And the answer to B, part 3, and just write it in so that you remember what that was, 0.0484. Calculate the relative formula mass. Now for this, we're dividing the mass by the MR, or the RFM, as I just tend to use. This can be rearranged to give us RFM. It's going to be 6 divided by 0.0484. And that'll give an answer of 124. So calculate the value of X. Well, we can work out this part. That's 106. So the difference between these two will be due to the water. 124 minus 106 equals 18. Well, the RFM of water is 18, so there's just one water molecule. X is equal to 1. Part C, I've got 3.36 grams of sodium hydrogen carbonate, which is this, and it's heated. So what we have to do is calculate the volume of carbon dioxide gas produced in cubic decimeters. Okay, so we've got to work out the number of moles of the sodium hydrogen carbonate. So that's going to be 3.36 over 84. That's 0.04. So 0.04 moles. We can then use the balance of numbers in the equation to look at the ratio. So 2 to 1. That means we're going to have half the number of moles of carbon dioxide. That'll be 0.02. We have to work out the volume. Anytime you work out the volume of gas, you're using 24 or 24,000, always. The units required are decimeters cubed, so that means we will use 24. The volume of carbon dioxide is going to be 0.02 times 24. That equals 0.48. Remember, the equation here is number of moles equals the volume of gas over 24. So I've just rearranged the equation to give me volume. So it's going to be moles times 24. On to the last page then of questions. Use Avogadro's law to calculate the volume of CO2 formed in cubic decimeters when 150 cubic decimeters of pentane undergoes complete combustion. Okay, well, Avogadro's law, equal volumes of gases at the same temperature and pressure contain the same number of molecules. Now, if there are 150 cubic decimeters of pentane, we just simply use the ratio. So you can see it's 1 to 5. So just multiply this value by 5. And that's 750. That's all you have to do there. E part 1. State the common name for calcium hydroxide solution, and you're told that calcium hydroxide solution is used to test for carbon dioxide gas. Well, that's obviously lime water. And part 2, then to finish, describe what would be observed when carbon dioxide gas is bubbled through the lime water, which we've established that's what this is. Well, the first thing that would be observed is that the lime water will change from colourless to milky. You could see a white precipitate there. But the question then goes on to ask until the carbon dioxide is in excess. So when you bubble carbon dioxide into lime water, you'll first see that milkiness appearing. But if you keep on bubbling carbon dioxide into it, that precipitate will disappear, or that milkiness will disappear, and it'll form a colourless solution. Now just write in the equations that's happening. You don't need to write this down in your answer. But the first part, the colourless to milky, that's going to be calcium hydroxide reacting with the CO2, given calcium carbonate. Now that's the solid. That's what makes it go milky. And then water is formed. So in the second part, why does it then turn colourless if you keep on adding carbon dioxide? Well, that's because the calcium carbonate, remember that's the milkiness that's in the water, and the carbon dioxide is being blown into it, actually turns it into calcium hydrogen carbonate.